Hello everyone, welcome back to my YouTube channel. In today's video, we are going to discuss about mathematics and its real-world problems. Our today's topic is Newton's Raphson's method, trapezoidal rule, Simpson's 1/3 rule, Simpson's 3/8 rule, Newton forward and backward interpolation, divided differences. So let's start with the first numerical method, that is Newton-Raphson's method. It is also an iterative numerical technique which is used to find the approximate roots of real valued functions. It's particularly used for finding solutions to equations that might not have exact analytical solutions or where analytical methods are difficult to apply. Its primary application of Newton-Raphson's method is to find the roots of nonlinear equations. These equations may arise in various scientific and engineering contexts, such as solving for equilibrium points in physics, chemistry, and biology. The second application is optimization. It is also used to find the critical points of a functions which are often used in optimization problems. It can also be used to find the maximum or minimum values of a functions in various fields. The third great application of Newton-Raphson's method, it is also used to solve the real world phenomenon. It is used to solve circuit analysis, fluid dynamics, structural analysis, and many other engineering applications. The next one is trapezoidal rule. The trapezoidal rule is a numerical integration technique which is used to approximate the definite integral of a function over a specified interval. It is particularly useful when you have a function for which it is difficult or impossible to find an analytical solution for its integral. So basically, the trapezoidal rule is used to approximate the area under the curve of a function by dividing the interval into small trapezoidals and summing up their areas. Their main application is to approximate the definite integral of a function. It can be used to deal with the functions that can't be integrated analytically. By dividing the interval into smaller segments and approximating each segment area as a trapezoid, you can estimate the integral value. The second major application of trapezoidal rule is it involves calculation of areas, lengths, volumes, and other quantities that are described by mathematical function. It can also be used to numerically solve problems related to motion, work, energy, and more. The next one is Simpson's 1/3 rule. It is also known as Simpson's rule or the parabolic rule. It is also an integration technique which is used to approximate definite integrals of a function over specific intervals. It provides a more accurate approximation compared to the trapezoidal rule. It also, especially for the functions that are relatively well behaved and smooth within the interval of interest. This rule approximates the function using quadratic polynomial, that is the second degree, within the subintervals. And the greatest application of Simpson's 1/3 rule, it can be applied to estimate the area under a signal curve to compute the various signal characteristics, that is total energy, average, value, and the power. The second Simpson's 1/3 rule application is that it can be used to approximate well by the quadratic polynomials, but it may not perform as well for functions with rapidly changing behavior within the interval. The next numerical method is Simpson's 3/8 rule. It is also an extension of Simpson's 1/3 rule. It is used to approximate definite integrals of a function over specific intervals. It provides even more accurately approximations by using cubic polynomials, that is the third degree, within the subintervals. While Simpson's 1/3 rule uses quadratic polynomials and is suited for approximating smooth functions, while 3/8 rule can handle functions with more complex behavior. And the applications of it are there complex behaviors are often encountered, Simpson's 3/8 rule can be used to accurately estimate quantities related to motion, forces, energy, and other physical phenomena. It's especially helpful when dealing with functions that exhibit oscillations or nonlinear behavior. Simpson's 3/8 rule is considered a more advanced numerical integration technique compared to the simpler trapezoidal and Simpson's 1/3 rules. It's frequently employed as a part of numerical analysis method for approximating integrals and solving differential equations. The next numerical method is Newton's forward and backward interpolations. They are used to approximate values of a function between the known data points. These methods are particularly used when you have a set of discrete data points and you want to estimate values at points that lies between those data points. These both methods use polynomial interpolation to achieve. And the applications of Newton forward and backward interpolation are it is used in the studies involving projectiles, trajectory calculations, motion analysis, oscillations. You might have discrete data points representing positions or velocities at specific time intervals. So, forward interpolation can be used to predict intermediate positions or velocities at non recorded time points. When analyzing geographical data such as elevation measurements at specific points, forward interpolation can help estimate elevation values for locations between the measured points. In historical studies, you might have data points representing certain events or measurements at different time periods. Backward interpolation can help fill in missing data points or estimate values that occurred before the earliest recorded data point. The next and the last numerical method is divided differences. These are used primarily in the field of numerical analysis and interpolation. They provide a way to generate coefficients for the polynomial interpolation, particularly in the cases where you have a set of data points and want to approximate a function that passes through these points using a polynomial equation. Differences are extensively used for polynomial interpolation. Given a set of data points, you can use dividend differences to compute coefficients for constructing an interpolating polynomial. This polynomial can then be used to approximate the values of the function between the given data points. Dividend differences can be employed to find the coefficients for fitting a polynomial curve to a given set of data points. This is particularly used in the fields like engineering, physics, and data analysis, where you want to find a polynomial equations that closely represents experimental or observation data. I hope you find this video informative. Thank you for watching and stay tuned for more such videos.